Okay. So it is almost 4 minutes to start. So let me just start by introduction. Hello, a very warm good morning to all of you. Greetings from Christ College Autonomous Irinjalakuda, Thrissur, Kerala, India. I am going to welcome all the participants and the resource persons. And let me introduce myself. I am Dr. Shaju KY, head of the department, also vice principal of the college. And this is a special occasion for us to celebrate our jubilee. Our department completed 60 years. And we are celebrating with the international webinar series. And the first one is today. Now we are going to inaugurate the Jubilee celebrations by Professor Dr. Paul Urbach from Netherlands. So my duty is to welcome you all, dear participants, my dear friends, my colleagues. Dr. Babu has come. Good morning, Babu. So, I will introduce our principal, Reverend Father Dr. Jolie Andrews CMI. He also belongs to physics department. He is very young and very dynamic personality and very actively supporting the activities of the department. And he is the president of this meeting. And on behalf of everybody present in this webinar, I welcome Dr. Father Jolie Andrews CMI to this webinar. Thank you, Father.
Thank you so much. Thank you.
Next, I have to welcome today's resource person, a very eminent personality, Dr. Paul Urbach from Netherlands. Only one thing is enough to show his caliber. He was the president of European Optical Society for the last 2 terms. I think everybody knows that European Optical Society is very active and very prestigious organization, which was presided by our resource person, Dr. Paul Urbach. So he is very active in research, very kind-hearted to accept our invitation, and Dr. Paul will inaugurate our Jubilee celebrations. And on behalf of everybody present in this meeting, I wholeheartedly welcome Dr. Paul Urbach. Sir, are you hearing?
Yes, I can.
Thank you, sir.
I will try to share my screen now and start the inauguration.
Wait, sir. Before that, let me welcome the participants also.
Okay.
So we have more than 300 participants in and around the world. And I take this opportunity to welcome all the participants to this webinar and all the greetings from Christ College Autonomous Irinjalakuda, Kerala, Thrissur, India. welcome all the participants. Now, the president of the meeting, Dr. Reverend Father Dr. Jolie Andrews, will speak few words about the college as well as the Jubilee programs. Father, please.
Okay. Am I audible and am I visible to everyone?
Yeah.
Okay, thank you. So now it is a very prestigious occasion for the Department of Physics for organizing this international webinar on super resolution with far field optics by Professor Paul Urbach, coming from the Netherlands and from the Optical Center. And he's also the past president of European Optical Society. And I have here and eminent personalities, our retired professors, the present professors, the students, representatives, research scholars, everyone, and especially Dr. K.Y. Shaju, the vice principal and the present HOD of our department. I make a few words about the Christ College. The Christ College started in the year 1956 by the Devamata province of Carmelites of Mary Immaculate, and this is an indigenous religious congregation founded in 1831 by Saint Kuriakos Elias Chavra, who was a very saintly priest and a versatile genius who saw the education as a tool for liberation and for the development. Now, the Christ College is a minority institution and re-accredited by NAC with the highest grade, and has been dedicated to Christ, and as its motto the Jivit Prabha, which means the light of life. The Christ College is a part of the century-old tradition of CMI education, which offers an ideal vision of education that is aware of and responsive to the challenges of the nation's present situation. Now, the college became one of the prominent epicenters of the academic training thanks due to the visionary leadership given to it by its first principal Padma Bhushan, Father Gabriel. College has at present 27 UG programs, 16 PG programs, and 11 departments offering research, because we are having 11 departments having research. Now, college also offers 21 certification programs and has at present 3,860 students, perhaps the largest number in Kerala. College has also entered into MOUs with the University of Zululand, South Africa, and Leibniz Institute of Applied Geophysics in Germany, which presents our students with a possibility of an international exposure. Now, I'm very happy to say I'm also a member of the physics department. We are celebrating the Diamond Jubilee of our department and of our UG program. We are also at present, we are also celebrating the Silver Jubilee of our PG program. And now it has been 10 years by which we have started our research program in physics. Now, at this occasion, especially remember our first HOD, Professor P.I. Paul, for his great leadership, which is given to our department now. He's, I think, joining with us now. His blessings are always with us. I also remember Father Joy Watoli, Professor E.K. Narayanan, Father Vijay Kumar, Father Alex Uken, who are also the members of our department who have gone for their heavenly rewards. I, in this special occasion, very much remember the contributions that has been given by all our retired staff members, our non-teaching staff members, the present and those who are retired, in a very special manner when we are celebrating this Jubilee. And now a word about the great things which we have done once we became a research department. At present, we have got 13 research students, and 6 are on the process of, after above these 13, the 6 have also been in the process of completing their research. We are actively doing research in the metamaterials, sensors, simulation studies of optoelectronic devices having organic and perovskite solar cells in superconductivity, semiconductor thin films, nonlinear optics, and in spectroscopy. And the last 10 years, we have already got 196 national international publications, which is a big number. I especially appreciate 130 paper presentations. 4 have submitted their PhDs, and 3 have been already awarded the PhDs. Interestingly, tomorrow we will have an online PhD viva of one of our research scholar. So especially appreciate the work that has been done by all our research guides in a very special manner. Also remember Dr. VP Joseph, who had pioneered the research when we became the research department. Now, I also in a very special way remember the PAC. PAC is an association, physics association, an alumni association we have started recently. I especially mention the name of our vice principal and our present HOD, Dr. K.Y. Shaju. He was very instrumental in organizing all our students around, and as a result of it, we have already started our lab renovation work that is in full process now, and already more than around 3 lakhs has been collected from completely from the students. I especially remember the generous contribution of the family of P.I. Paul. P.I. Paul sir and his family contributed very generously around 50,000 rupees to our department. I especially remember them in a very special manner when we are celebrating this Diamond Jubilee. We have a very happy notion to say that our present VC of the University of Calicut is Dr. Jairaj, and he was also a prestigious alumni member. And I know Dr. Babu Varghese is here. It's from the first batch of our physics students. Now, in this wonderful occasion, I'm very happy to be present here as a principal of this college. I'm really happy about our physics department for the wonderful things which are done. So wish you all the best for this webinar series. We are inaugurating this webinar series now, and we have got a wonderful personality here to have this webinar inaugurated by Professor Paul Urbach. You would have already read some of his wonderful papers. So have you a wonderful time today in this webinar. May God bless you all. Thank you very much.
Thank you, Father. Thank you, Father, for your blessings and good words. Now, Professor Paul, Dr. Paul will inaugurate and he will continue with his talk. Paul, sir, please.
Okay. Thank you very much, dear Chairman Dr. Andrews, and dear Dr. Shayu, dear organizing committee. I thank you very much for the honor of inviting me today to this special webinar. I only congrats with its Diamond Jubilee. I happen to know one of the first members of the first batch of master students of your Christ College Department of Physics was Dr. Babu Varghese, which was already mentioned. He is a very famous physicist in the Netherlands. He is one of the leading bio-optical scientists in Philips research, and he is well known for his expertise in optics. I like to inaugurate the celebration herewith, and I wish you a very joyful event in the coming time, and also a lot of success and accomplishment in the years to come. I would have liked to be present, actually. I have never visited the south of India myself before. Unfortunately, we are now in a circumstance that nobody of us can travel, but maybe in the future I find occasion to be able to visit you. So thank you very much, and again, all success for the future. Can I now?
Thank you, sir. Thank you. Thank you, sir. Yes. You can present. No.
Okay, I will try. Do you see my screen?
Yeah, we are seeing.
Okay, thank you. So this is my first slide, so that you, in case you could not hear me, at least you see my congratulations.
Thank you, sir. Thank you. Thank you very much.
I will now continue with my presentation. If there is some trouble that you cannot hear me, please let me know. So I would like to say something about resolution in optics, an old topic. I will also say something about super resolution, but all the things I'm talking about are with far field optics. And the reason is that the applications of optics are mainly using far field techniques. And so it is important to consider for applications in industry, for example, to study the resolution that is achievable using far field techniques. Now, if I talk about optical imaging, it is maybe good to define what I mean by this. I mean transfer of information about an object to a detector by optical fields. So that means by electromagnetic fields, basically. So imaging this is a broad definition of imaging. It can be any information, but of course, the more, the better. Now, since the transfer of information is by electromagnetic fields, the information that we actually are sensitive to in optics is the permittivity function of the object. And the interaction of light with the object is, of course, an electromagnetic scattering problem. In classical imaging, we try to realize a kind of a copy of the object in the plane of the detector. In computational imaging, the detector can be anywhere in space, not necessarily in an image plane. And the data that are measured are then processed by a computer and the object is reconstructed. A third way of imaging, of transfer of information, is scatterometry, where usually the detector is in the far field. Now, if we talk about, but any three of these modalities are considered by me in this talk. So optical imaging is considered in the broad sense. If we talk about resolution, then a sensible thing to ask ourselves is what spatial frequencies of the object influence the measurements. So if we want to quantify resolution, this is a very sensible approach. We will look at spatial frequencies of the object and see which spatial frequencies influence the measurements. So I will be talking a lot about Fourier transforms because those give you the spatial frequencies. If you try to achieve super resolution, then typically the problem of reconstructing the object is ill-posed and very sensitive to noise. What will not be considered in this talk is I will not consider polarization because the main ideas can be conveyed to you by looking at the scalar theory. I also will not talk about partial coherent light. All the light will be fully coherent and monochromatic. And also nonlinear effects like self-focusing in nonlinear media, STAT and PALM, I will not consider. I only look at classical linear optics in this talk. Just to fix notation. So as I said, no polarization. So all optical fields are scalar and I will denote them by a capital U. They are time harmonic and I use complex notation where the capital U in normal type is the complex field. The modulus of that complex field is the amplitude at the position R considered. And the argument of the complex number is the phase at that position. So this is the notation that I will be using. I will use complex fields. Now, the first thing we would like to consider to be able to talk about resolution is the following problem. Suppose that we have an object in the half space z smaller than 0. And if you look at the picture below, you see the object in the left half space to the left of that plane, which is the z is 0 plane. And we illuminate that object and we get a scattered field, which I denote by U sub S. And that scattered field is going to propagate to the right. And the first problem we want to look is, suppose that we know the field in the plane Z is 0, that is the gray plane in the picture. Can we find the field anywhere to the right of that plane, assuming that we have a uniform medium with fixed refractive index taken to be 1, for example, air? Now, to solve that standard problem, first of all, we note that the scattered field satisfies the Helmholtz equation. And K is here the wave number. And if we want to solve this problem, it is quite sensible to do a Fourier transform with respect to the X and Y variables. Those are the variables with respect to which the geometry is infinite. So we do a Fourier transform and we find very easily a solution in terms of what is called the angular spectrum decomposition. So you see here a formula for the scattered field in any point X, Y, Z to the right of the plane Z is 0. And you see it's an integral over spatial frequencies Kx and Ky. Basically, this integral extends from -infinity to +infinity. We cannot assume that the spatial frequency range is finite. It will be infinite in general. And you see it is a superposition of plane waves with wave factor Kx, Ky, Kz components, where Kz is linked to Kx and Ky by this square root below here. The reason that you see a plus sign here in front of the square root is that the wave propagates to the right in the positive Z direction. So as I said, we have a superposition of plane waves with amplitudes given by the Fourier transform of the scattered field in the starting plane, in the Z is 0 plane, where we assume the field to be known. And so the recipe of the angular spectrum. So the recipe of the angular spectrum method is very simple. You just Fourier transform the assumed known field in the Z is 0 plane. And for every spatial frequency Kx, Ky of that Fourier transform, you propagate the field to another plane Z is constant using this plane wave expression. And then you add all these plane waves up. So if you go to very large distances, you will obtain in this way the Fraunhofer approximation. The Fraunhofer approximation, which says that at large distances from the starting plane, you will actually get for your field a Fourier transform, as shown here, with spatial frequencies in that Fourier transform that are given by the ratios Kx over Z, Ky over Z. And these spatial frequencies, you can easily show that for Z large, that these spatial frequencies in the far field that influence therefore the far field are never larger than the wave number K. In other words, if you look in the scattered far field, you see that it depends on the Fourier transform of the near field, of the scattered near field in the Z is 0 plane, but that spatial frequencies that influence this far field are limited by the wave number K. So here you see an example of illuminating a screen with an aperture in it. And you look in the far field, in the Fraunhofer far field, and what you find is this pattern here, which is a sinc function as function of X over Z, this angle. And that is the Fourier transform of the slit, as you all probably know. So let's go back to the general case, the angular spectrum. Not necessarily to infinity. We're not going to the far field necessarily. We can go to any point x, y, and z to the right of the starting plane. Now, as I said already, this is an integral over infinite extension of kx and ky from minus infinity to plus infinity. And we distinguish between two areas. The first one concerns the propagating waves for which kx and ky are inside a circle of radius k. If that is the case, then the z component of the wave factor, kz, as you can see from the square root expression, is real. And so not only kx and ky is real, but also kz is real. So we have a real wave factor and a propagating plane wave, therefore. However, if kx and ky are outside of this circle, then the square root is imaginary. As you can see here, the kz has an I in front of the square root, which is the positive square root now, but it's an I in front. So it's purely imaginary, and which means that in the z direction, the wave is not propagating anymore, but due to the fact that the lateral spatial frequencies kx and ky are so large, the kz, the z dependence of the wave is exponentially decreasing. I note in passing that evanescent waves, as these waves are called, evanescent waves, as they lose their amplitude in the z direction exponentially fast, they also do not propagate energy in the z direction. Evanescent waves do propagate energy, but they propagate energy in the lateral direction, kx, ky direction, not in the z direction. So to summarize, we have in the reciprocal space, in kx, ky space, in the angular spectrum space, we have two regions, a yellow circle inside of which we have the propagating waves, which keep their amplitude. They change their phase upon propagation, but they keep their amplitude. And we have outside of that circle of radius k, we have evanescent waves which lose amplitude exponentially fast. Now, this implies that after a propagation of only a few wavelengths, we will have lost almost all the amplitudes of almost all the evanescent waves. And since the spatial frequencies of these evanescent waves are larger than k, it means by the uncertainty principle, or by a property of the Fourier transform, which is equivalent to that, that information about the object, about the field, the scattered field, that is smaller than the wave, because this information, this high spatial frequency, this small details, smaller than lambda, can only show up in the evanescent waves, in the evanescent components, and they are basically lose their amplitude. So the basic information transformation that we have in optics is limited. We cannot propagate details, information about details that are smaller than the wavelength. And this is a basic property of propagation of optic fields. It has nothing to do with how good your optical components are, how good your lenses are. You already lose this information simply by propagation in free space. Now, in practice, we do have optical systems, we do have lenses, we do have objectives. And it means that in practice, not all the propagating waves can contribute to the transfer of information. In practice, only a limited cone of plane waves can contribute. And that cone and the angle of that cone defines the numerical aperture of the system. If you have a lower numerical aperture, then the spatial frequencies of the propagating waves that contribute to the imaging is smaller. If you have a higher NA, a larger part of the propagating waves can contribute. So in practice, the circle, yellow circle of propagating waves cannot all contribute, but they are limited further. The radius of the circle is reduced by a factor which is called the numerical aperture, which is a number smaller than 1. So the real radius that we are dealing with is k times NA. And that means that the resolution that we can obtain is not lambda in practice, but it's a bit worse. It's lambda over NA, with NA is a number smaller than 1. So any features smaller than lambda over NA cannot be recovered in the image. So this is the start with some basic properties I wanted to summarize. There is a new development which is called lensless imaging, where people measure amplitude and sometimes also phase by interferometric method, by holography, for example, where they try to measure the far field in some plane, not an image plane, and then because they know amplitude and phase in that plane, they can back propagate the propagating waves. And so what is obtained then is a copy of the object that is filtered, because all the evanescent waves are lost. We cannot retrieve those. We cannot back propagate those. That would be too unstable. And so we have a band limited version of the object. Actually, lensless imaging, which is very important for extreme UV and for X-rays nowadays. So for example, it's used in modern lithography for modern integrated circuits manufacturing. This lensless imaging doesn't always require that the phase is measured. You can also do back propagation by an iterative phase reconstruction on the computer. An important example is a method by FINUP, which doesn't always work, but there are better methods. But basically, FINUP methods is easier to understand, where an iterative reconstruction. So basically what you do is you have an object which consists of an amplitude and a phase, the amplitude in red and the phase in blue. And you measure somewhere in the far field, for example, the intensity. So you measure only intensities in the far field. And then using the fact that you know where the object is, so you know the region in space where the object is, and furthermore, you have the intensity in the far field, you can apply a reconstruction algorithm which gives you basically both amplitude and phase of the object. So that's lensless imaging. I skipped this. So I now return to the question of resolution. So far, I have been talking about a scattered field and how it propagates and what information of the scattered field can be propagated. And as we have seen, only details that are larger than the wavelength can be transferred to can be propagated. Now, the actual object is not the same as the scattered field, of course. And often in optics, we model an object by a reflection or a transmission function. Now, let's look at the reflecting object. Often in optics, we say, look, the object is being illuminated, say by a field U sub I. And the scattered field is simply obtained by multiplying that incident field U sub I by a reflection function or a transmission function. I'm looking at reflection here. That's, of course, a very simple model, but it's often used. And now the question is, what information about R, about the reflection function, can actually be retrieved? Now, if you would illuminate the object by a perpendicular incident plane wave propagating along the z direction, the optical axis, then actually you have a constant field with which you illuminate. And so basically the Fourier transform of the reflection function R is the same as the Fourier transform of the scattered near field. So we assume that the object is in the z is 0 plane, right? So basically the Fourier transform of the reflection function is the same as that of the scattered near field. And hence, what I have been saying about information transfer of the scattered near field applies also to the reflection function. In particular, the limit of resolution is given by lambda over NA. So any information of the reflection function, any details that are smaller than lambda over NA cannot be recovered after propagation. However, if you would illuminate the object by a strongly oblique plane wave in the limit so oblique that if you look at the spatial frequency of the plane wave, let's take the x component almost equal to minus k, minus the wave number. You can't make it larger than the wave number, of course. So this is a limiting case. If you would do that, then something better is achieved, because then the Fourier transform of the scattered field is equal to the Fourier transform of the reflection function times the incident field. And by the convolution theorem, that is the Fourier transform of the reflection function convoluted with the Fourier transform of the incident field. And because that is an oblique plane wave, it basically means that you get your Fourier transform of the reflection field, reflection function shifted over k in this case, because we have such an oblique illumination. Now, of course, as I said before, information about spatial frequencies of the scattered field are limited by k and a. You cannot transfer information of kx and ky outside of that circle. But you see that for kx and ky inside that circle, there are the spatial frequencies that influence the far field of the reflection function are larger. It's kx plus k that you see here occurring. So what we find is that actually the spatial frequencies of the reflection function that can influence the far field are now larger. They are up to 2k. So by oblique illumination, by a plane wave which is very oblique, you can get a resolution for the reflection function that is almost twice as good as if you would illuminate by a perpendicular plane wave. So in general, structured illumination can give you a higher resolution for your reflection or transmission function. And in fact, you find that the resolution is enhanced by a factor of 2 maximum. So it becomes lambda over 2 NA instead of lambda over NA if you use very oblique, strongly focused spot. So examples are very well known in industry. For example, in optical recording, a very tightly focused spot with a high NA is used. That spot contains very strongly oblique plane waves. And those plane waves gives you a better resolution, a higher resolution that you otherwise would see. You can see smaller pits with the same wavelength than you would be able to see if you would be so foolish to illuminate the disk by a plane wave of low NA. Another example is a confocal microscope where the sample is scanned by a focus spot, again giving higher resolution because the focus spot consists of very oblique plane waves. Another example is total internal reflection microscopy, where you illuminate by 2 plane waves which are very strongly oblique. They are above the critical angle of total internal reflections. For example, this is glass and above here is air. You put the sample on the glass. Where you illuminate with is a standing wave with high spatial frequencies. And again, this gives you higher resolution, higher spatial frequencies of your reflection or transmission function can be transmitted in this way. Now, having said that about the reflection function, I started my talk talking about the permittivity of an object. And I said that basically information that we can transfer is, and the information that we can obtain is the permittivity contrast of an object. So say the delta epsilon, the epsilon compared to the background of the, what is the relationship between models with reflection functions in optics, simple models, and electromagnetic models where you really use the permittivity contrast? What does it mean if I say that the reflection function can be obtained only up to lambda over 2Na? What does it mean for the permittivity contrast? Well, actually, there is a very tight relationship between the two. To show you that, and therefore, all I have been saying about the reflection function actually also applies to the permittivity contrast, which is the real thing, the real object, the real thing that describes the object electromagnetically. And the reason for that is that if you use Maxwell's equations, you can find that these Maxwell's equations for the scattering problem is equivalent to an integral equation, which is called the Liebman-Schwinger equation, which is also known from quantum mechanics. And it's an integral equation for the total field, the sum of the incident and the scattered field. And you see this integral equation is written down here. It consists of an incident part plus an integral, which is the scattered part, a scattered field. And that integral is an integral over the object. And you see it is a convolution integral, and G is basically the field of a dipole, a spherical wave. So we have the integral gives us a superposition of spherical waves. The scattered field is a superposition of spherical wave inside the object, and the amplitudes of these spherical waves are given by the product of the permittivity contrast, delta epsilon, and the total field inside the object. Now, we don't know that total field. We only know the incident field. We don't know the total field. But this is an integral equation for the total field. If you can solve this equation, then you can substitute the total field again, and you find the scattered field. So this is what Maxwell's equations tells you about the fundamental interaction of light with an object. So this is the fundamental approach in optics. Now, if you look at an approximation of this equation where you replace the total field in the object, U total here in blue, by the incident field, that's an approximation. That's not correct because you discard the scattered field inside the object. It's just a first order approximation. If you do that, you obtain this equation where now in the right hand side you see the incident field in blue where we previously had the total field. And of course the incident field is known. So in principle we can calculate this scattered field now. This is called the first Born approximation. If furthermore you assume that you have a thin object, that's the second approximation I make. If you have a thin object, you can replace this three-dimensional integral, which extends over the full three-dimensional object. You can say you can limit it to 2 dimensions because the object is thin in the z direction. You only have a 2-dimensional integral now. And then if you Fourier transform this integral, this approximation of the scattered field, if you Fourier transform it, you find that the Fourier transform of this scattered field is almost the same as, it's proportional to, the Fourier transform of the permittivity contrast multiplied by the incident field. Now, if I may recall what we had for the reflection function, we had in equation 1 up here, very similar. The Fourier transform of the scattered field of the object is given by the Fourier transform is equal to the Fourier transform of the product of the reflection function and the incident field. That's equation 1, you see? We have now the same equation in the electromagnetic case. In equation 2, we have the Fourier transform of the scattered field is equal to the Fourier transform of the product of the permittivity function and the incident field. So the permittivity function simply plays the role of the reflection function had previously. So anything I have said about the resolution that I can attain for the reflection function is also true for the more rigorous permittivity contrast function. So to summarize, the Fourier transform of the scattered field in the first Born approximation for a thin object is given by the Fourier transform of the product of the permittivity function and the incident field, like we had previously the product of the reflection function and the incident field. So the conclusion is that if we use the first Born approximation, which is not an exact formulation, but an approximation, the maximum resolution that we can obtain for the permittivity is the same as we had for the reflection function. So it is lambda over 2NA. That's the maximum. Does that mean that lambda over 2NA is absolutely the maximum possible resolution that we can obtain with far-field optics? It seems to suggest yes. The answer should be yes. However, we have been making an approximation here. We have been using the first Born approximation. The actual scattered field is given by the integral with not here the incident field in blue, but the total field in blue. And so we have to be a bit more careful. And if we look at multiple scattering, I compare here the first Born approximation for the scattered field with the incident field here in blue, and the exact formulation for the scattered field where we have the total field in blue under the integral, which of course in principle a priori is unknown but can be solved numerically. Then we note that in fact, using the exact formula, the Fourier transform of the scattered near field is given by basically the Fourier transform of the permittivity contrast and the total field, not the incident field, the total field. And now notice that in some cases, the total field can have very high spatial frequencies. The incident field cannot have such high spatial frequencies because it is limited by the fact that it is generated by a source further away. So it's obtained after propagation over a macroscopic distance, and therefore its spectrum is limited by K, in practice by K and A. But the total field is a field inside, and it contains contributions of dipoles excited in the medium in influencing each other, exciting each other. So in principle, there is the possibility that this total field contains high spatial frequencies, much higher spatial frequencies than the incident field. And that gives a route to super resolution. So again, the Fourier transform of the scattered field is the convolution of the Fourier transform of the permittivity and the Fourier transform not of the incident, but of the total field, if you look at the accurate theory. And because this Fourier transform of the total field can have, in some cases, very high spatial frequencies, which have a strong amplitude, and this is in particular the case when you have a plasmonic resonance in a metallic particle, then you can see that because this Fourier transform of the total field has very high spatial frequencies of delta epsilon can influence the Fourier transform of the scattered far field. Just because of this convolution, high spatial frequencies of one factor can be compensated by high spatial frequencies of the other factor, and then give low spatial frequencies in the far field. So in this way, high spatial frequencies higher than K, the wave number, of the permittivity function can in principle influence your measurements in the far field. But it can only be realized in special cases. First of all, you need a resonant field, as I said, something like a plasmonic resonance field, to get these high spatial frequencies of the total electromagnetic field inside the particle. Or, and this is another possibility, you may be able to use very diverse illuminations, much more diverse than the oblique ones that I mentioned before, which cause very different scattered fields, which are very sensitive to some parameters of the object that you want to retrieve. That's another way of trying to achieve super resolution. But in any case, whether you use resonant fields or you use very diverse illuminations, in practice you can only retrieve a small number of parameters with super resolution. Only a few parameters can be retrieved with super resolution. For the rest of the object, you need a priori knowledge. So all the other aspects than these few parameters must be known a priori. So in some way, you can retrieve high resolution, super resolution parameters, some shapes, but that has to be compensated by more knowledge about other aspects of the same object. It is always very important to consider statistical analysis to, for example, to try to estimate the so-called Kramer-Rao lower bound for the retrievement of the parameters, because whatever you do in super resolution, it is very noise sensitive, and you have to quantify the accuracy of your retrievement with this kind of statistical analysis. That's just a side remark that I want to emphasize. I give you now two examples very briefly and close my talk about these two approaches: resonant fields to achieve super resolution and diverse illuminations. The first example is resonance fields. I look at two gold bars which have a cross-section of 50 by 50 nanometer. Both of them have a cross-section of 50 by 50 nanometer. They're identical, very close together. The distance between them is smaller than 50 nanometer. And we illuminate these golden bars, very small nanoparticles, by a focused spot with a very specific polarization, so-called azimutally polarized spot. So in the end of my talk, I'm talking about polarization. This particular polarization field is important for the effect that we want to achieve. Now, if the focus spot, the center of the focus spot, is exactly between the two gold bars, everything is symmetric. And so just as much light is being scattered to the left as to the right of the gold particles. But if you move that spot slightly off center, that azimutally polarized focus spot, and you use a wavelength for which the gold particles are at a resonance, a plasmonic resonance that's necessary to achieve the effect, that's the resonance which we need. If you move the spot slightly off center, then suddenly you see that almost all the light scatters in one direction, to the left in this case. And if you move the spot to the left, the scattered light goes to the right. You see here a radiation diagram below. Below here, you see an experiment where this is confirmed. In the center picture, you see the two gold bars being illuminated in the symmetric configuration. The spot is exactly, the center of the spot is exactly in the center of the two bars. And we have made, on the substrate, we have made two small scattering particles at some distance to the left and to the right, so that we can see how much light is being scattered to the left and to the right. And this scattered light is rescattered by these small objects, and it goes into the detector. Otherwise, we couldn't detect that scattered light. You see it's completely symmetric in the center. But if we move the spot a bit off center, you see that the light is almost completely scattered to the left, or in the right picture, to the right almost 100%. So a very small change of the illumination, a very small displacement of the bars, you can also say that, can give you a very strong effect in the far field. In spite of the light that we use, which is 750 nanometer. The last example, very briefly, is again an example where very few parameters, but with very high resolution are retrieved. I'm looking here at a cylindrical bar of silicon on top of a glass substrate. And the cylinder has an elliptical cross-section with major and minor axes A and B, as shown in the picture. And we want to retrieve the size of A and B. And A and B are roughly of about 10 nanometer only. The wavelength that we use is about 1 micron. We illuminate from the top, which is air, and measure through the glass. And by using two types of illumination, we can retrieve both A and B. If we illuminate with a perpendicular incident plane wave from the top, which is polarized in the X direction, then we can retrieve B without knowing A by looking in the glass at the intensity ratio between supercritical angles and undercritical angles. The supercritical angles are the angles under which light is radiated in the glass, which come from evanescent waves in the air. And you can imagine that if the particle is higher, then these evanescent waves have a longer path to the glass, and the evanescent waves in air will have been damped more, exponentially decreased, and therefore the light scattered in the supercritical angles will be less. So by comparing the light scattered in the glass between the supercritical and the undercritical angles, you can very sensitively determine B, the height of the particle. And once you have the height of the particle, you can illuminate the particle completely differently by a standing wave, which is p-polarized and which you scan over the cylinder. You see it in the right upper picture. You see the polarization state that you can achieve in such a standing wave when it's p-polarized. Basically, you can achieve any polarization state in such a standing wave. And by scanning that, and by scanning this particle, you can retrieve the ratio between A and B. The ratio between A and B. And since we already had B, we can also find A. And the accuracy is, as you can see in this lower picture here, is below 5 nanometer. In fact, it is about 1 nanometer. Only 2, but with a very, very high resolution. So the summary of my talk is optical imaging is transfer of information of an object to the detector. And information here is permittivity, is the permittivity function. We can sometimes use the reflection function R or the transmission function because it's easier to work with. But basically, any statement about the reflectivity function and the transmission function is the same as talking about the permittivity function. Any information smaller than the wavelength is already lost during propagation, irrespective of the quality of the optical components in your system. If you use oblique illumination, you can have a larger, slightly larger resolution, factor of 2 better than if you have perpendicular illumination. It's lapped over 2 NA in the best case. And only if you have a very strong multiple scattering in your object, which requires a small object, your resolution can be better. However, if you want to have super resolution, you can only achieve it in the far field if you try to retrieve small number of parameters of the object. Other parameters, other aspects of the object should then be known. And that is the end of my talk. Thank you for your attention.
Thank you, sir. That was a very wonderful presentation. Nice presentation. Now it is time for interaction. Participants can ask questions. Dr. Babu, Babu is there. Babu also can speak few words later after interaction. Yes, participants, please note that we will provide a feedback form and you have to answer, then we will give the certificates. Okay. Please, questions? Any questions, please?
Okay, I am Pradyumnan from University of Calicut. Hello, can you hear me, sir?
Yes, sir.
Yes.
Thank you, sir. Welcome,
Yeah.
sir.
Okay, I have a question. I already typed it. But is it possible to use high energy electromagnetic rays like gamma rays to measure material in the atomic scale? That is my one question. Because you already discussed about the resolution and other things. And also you mentioned the lensless imaging. There I have a question that can we use gamma rays for this?
In
Gamma-
principle,
Yeah.
The statements I made are relative to the wavelength. As long as the phenomena are described by Maxwell equations, it doesn't matter as long what the wavelength exactly is. But the fact is that details which are smaller than lambda over 2 in general cannot be retrieved in the far field. If you want to retrieve a specific parameter, a few parameters, 2 or 3, you may achieve higher resolution, but then you have to know know all the other aspects of your sample. So for example, if you want to use gamma rays and you want to retrieve information about the lattice of some material, that is possible if the lattice is of the order of lambda over 2 up to that wavelength, then you can retrieve those details.
So I am mentioning only atomic scale, like that maybe some angstroms, that range. And you yeah.
Yes, if you use X-rays with small enough
X-rays, of course.
wavelengths,
Yeah. Okay.
yes.
Yeah. And also you mentioned that
the problem with X-rays is a bit, if you want to retrieve, what I've been talking about is coherent light. So I'm always using amplitude and phase. And if you want to use phase information, which helps to get the resolution limits, to achieve the resolution limits, then in the X-ray case, there are not very good sources for coherent light at the moment, for coherent illumination. That's a practical problem.
okay, thank you, sir.
Any other questions, please? We have few more minutes for questions. You can type your questions also in the YouTube link. That will be answered later. If anybody wants any questions to be live, you can ask now.
This is Nandini here from BMS IT. I had a question related to how we can enhance the spatial resolution of far field optical imaging without going for photo bleaching aspects. Is there any other options available to enhance the spatial resolution of far field optical imaging, sir?
So in general, there is no general recipe, but as I said, you can retrieve some parameters with very high spatial resolution, but only if other aspects of the object are known. So I showed you an example of finding the size of an elliptical particle, but I know that it is elliptical, you see? I assume that I know it's elliptical.
Okay. Sir.
If you would say this can be any oval, it doesn't have to be an ellipse, and I need many parameters to describe it, I would not be able to achieve a resolution of 10 nanometer with a wavelength of 1 micron.
Okay. Thank you, sir.
Any other questions, please? If no more questions, Dr. Babu, can you speak few words? Dr. Babu?
I think Dr. Babu is muted. He's muted.
Yes, he is there. Muted. It is
Babu,
muted.
please.
I think you have to unmute.
Babu, unmute the microphone. Unmute the microphone, Babu.
Can you hear me?
No, yeah. Yeah.
Okay, sorry. I thought I was muted from the other side. So, dear Paul, dear Shaju sir, dear Reverend Father Jolie Andrews, and all the faculty members of Christ College, where I have my physics education for 7 years, and also all the participants of this webinar. It was a great pleasure for me to introduce, to bring Paul Urbach for this webinar. So a few weeks back, when Shaju sir contacted me asking for resource person, the first name that I came to my mind was Paul Urbach, and that's for an obvious reason. We worked together. I think we met 10 years back in a joint Philips funded project. We also applied for a Horizon 2020 European public funding program, where like 8 participants or organizations from Europe participated. And more recently, we co-supervised a PhD student. She will be finishing her PhD, defending her PhD in 2 months. So having said that, when Dr. Shaju, our Shaju sir, asked for resource person, I asked Paul, but my biggest concern was how can I convince Paul that to give a talk in a Christ College where he's remotely connected. But Paul was very open in all our collaborations and communications. He was always remain very helpful and supportive. And having listened to this talk for the last 1 hour, I felt like I was taken back to my graduation or post-graduation classes. All the theories, the derivations, because I spent like last 14 years more on the application side of biooptics. So again, thanks to Shaju sir and the management, especially to Father Jolie Andrews and all the faculties for organizing this webinar. Thanks to the participants for joining. And finally, Paul, many thanks. Thanks a lot for your time, for your patience.
It was my pleasure. Thank you very much for the invitation again.
Thanks,
Also,
Paul.
that was a great honor for us to have a wonderful resource person. If no more questions, we will move to vote of thanks by Dr. Xavier Joseph, who is the convener of the program. Dr. Xavier Joseph, please.
Can you hear me?
Yeah.
Okay. So let me introduce myself. I am Dr. Xavier Joseph, Associate Professor working at Christ College in the Department of Physics. So it's my privilege to express the vote of thanks for this session. Respected Principal, Reverend Father Dr. Jolie Andrews, respected Speaker, Professor Paul Urbach of TU Delft University, Head of the Department, Dr. K.V. Shaju, Dr. Babu Varghese, dear participants and my dear friends. Today, we are lucky to have an eminent personality, Professor Paul Urbach, as our resource person for the webinar and inauguration of the Diamond Jubilee celebrations of the Department of Physics, Christ College. He has given us a wonderful talk on super resolution with far field optics. Sir, you have enlightened us and opened the window of new possibilities of increasing the resolution limits beyond the value of lambda by 2na. On behalf of Christ College and all the participants, let me express our deep sense of gratitude to Professor Paul Urbach for accepting our invitation and sharing your ideas and findings with us. Thank you, sir.
Thank you. My pleasure.
Thank you, sir. Now, I would like to thank Reverend Father Dr. Jolie Andrews, our principal, for extending all his support for arranging this webinar. He is a member of the physics faculty, and we are happy, and he is an enthusiastic supporter of all the activities of the department. Thank you, Father Dr. Jolie Andrews.
Thank you, sir. You have wonderfully convened this meeting in a very good manner as a convener. Special appreciation to you also, Dr. Xavier. Thank you.
Thank you, Father. Next, I wish to thank Dr. K.V. Shaju, Vice Principal and Head of the Department of Physics, who is the backbone of all the activities of the department. Amidst the COVID-19 pandemic and the sudden lockdown in our place, he took all the efforts for the smooth conduct of this webinar. Thank you, sir. Thank you, Shaju, sir.
Thank you, sir.
I also wish to place my sincere thanks to all the esteemed participants for joining this webinar and making it a fruitful event. I would also like to express my special thanks to Dr. Babu Varghese, Senior Scientist in Personal Care and Wellness Division of Philips Research, Netherlands, for his help in arranging this webinar. He is our former student, and he is actually the link between the Department of Physics and the Professor Paul Urbach. So thank you, Dr. Babu Varghese. Thank you very much.
Thank you, Xavier, sir. Thank you very much.
Finally, I wish to thank all my colleagues in the department and the technical staff of the college for their active support and making this a grand success. So thank you all. So thanking you all once again, let me conclude. Thank you.
Okay, Paul sir, thank you very much. We are now ending this webinar. Thank you all. Thank you, participants. We will again come with another international webinar in the next coming weeks. And thank you very much.
Thanks, everyone. Thanks.
Thank you all.
Goodbye.
Thank you all once again.